So the biophysical chemistry, as we have discussed earlier, acids have sharp and piercing taste. And that was the first observation made by the people to make a distinction between acid and the base. Anything which has a sharp and a piercing taste, like a lemon or any other citrus fruits, people said that they contain acids. Later on, Lavoisier gave this idea: acidity of a substance is due to oxygen. And after that came Arrhenius, and Arrhenius gave the idea on electrolytes. And according to Arrhenius' theory, electrolytes, he spoke mainly on the dissociation of electrolytes. So the electrolytes can be divided into two types, namely strong electrolytes and weak electrolytes, depending upon their ability to get dissociated in aqueous solutions. When an electrolyte is put into water, an aqueous solution, if that electrolyte undergoes dissociation spontaneously, then that electrolyte is called strong electrolyte. Weak electrolyte is the one which is not getting dissociated even at infinite dilution. Normally, if you want to understand the electrolytes and the non-electrolytes, normally the following experimental setup is simply made. This is what I have also told you to make by yourself so that you can understand. Look here, just there is a small beaker in which two electrodes are dipped. And it is connected to the battery. Look here, this is the battery, the power source. So when you close the circuit, this is the switch. When you close the circuit, suppose if this is the negative terminal, the electron starts from here, it goes over there and goes across the switch and goes to the bulb, and then the circuit is closed when the solution is conductive. If the solution is not conducting electricity, then the circuit is open, the bulb will not glow. But the resistance of the solution depends upon how fast the electrolytes are conducting the electricity, or the quantity of the electrolytes that are conducting the electricity. Therefore, if this solution is containing electrolytes, the bulb will glow. If non-electrolytes, the bulb will not glow. Even in the electrolytes, for strong electrolytes, the brightness of the bulb will be high, and for the weak electrolytes, it will be dull glowing. And also when you promote the ionization, when the more and more ions are generated, the brightness will gradually increase. Now, in order to define the dissociation pattern in the case of strong electrolytes and weak electrolytes, if you take nitric acid, which is an example of a strong electrolyte, which will undergo dissociation immediately, and it will be found as a H plus and NO3 minus ions. And there is a complete dissociation. That is why the reaction is mentioned with a single-headed arrow. But in the case of nitrous acid, so here actually NO2 is supposed to be here. I have not written that, NO2. So HNO2, H plus, NO2 minus. An equilibrium sign is there, which means that the dissociation and association are taking place simultaneously. So that is the idea. H plus and NO2 minus, the dissociation is taking place simultaneously. So that is about the weak electrolyte. Next idea was given by Bronsted and Lowry. And according to the theory of Bronsted and Lowry, acid is a proton donor, whereas base is a proton acceptor. Acid is a proton donor and base is a proton acceptor. Later on, several theories came, but they were not popularized. The next popular theory is the theory of Lewis. And this Lewis said acid is an electron acceptor and the base is an electron donor. And another thing, this idea you should understand because many questions are asked on the basis of this, how to find out the conjugate acid pair, acid-base pair. Look here, look at the first example. This is sulfuric acid plus water. What happens? One H plus is given by sulfuric acid to water. So on the left-hand side, which is the proton donor, H2SO4 is the proton donor. So it is the acid. And the water is a proton acceptor. Hence it is a base. If you look at the right-hand side, if at all the reverse reaction is taking place, here the proton donor is H3O plus. This is having one proton extra. This is the proton donor. And the HSO4 minus is the proton acceptor. So on the right-hand side, this is the acid and this is the base, but we cannot call this is a real acid because this acid is generated because of this reaction. So this is called a conjugate acid. And this is called a conjugate base. So the acid on the left-hand side and its conjugate base, which is in the right-hand side, they are called conjugate acid-base pair. And also this is the base, this is an acid. Therefore, these two are called conjugate acid-base pair. Similarly, you can think of another equilibrium, ammonia. If you take ammonia with the water in liquid form, what will happen? Here, water is the proton donor because it donates one proton to nitrogen, ammonia, and it is making NH4 plus aqueous. So the proton donor is water molecule, hence it is an acid. Ammonia is a proton acceptor, hence it is a base. But if you look at the right-hand side, here, ammonium ion, NH4 plus ion is the proton donor, and the OH minus is a proton acceptor. Therefore, on the right-hand side, this is an acid, and this is the base. So what happens? The water and the OH minus are conjugate acid-base pair. Similarly, ammonia and ammonium plus ion are conjugate acid-base pair. But if you compare these two things, here water is acting as a base, here water is acting as an acid. Therefore, one single substance which can act as a base and as an acid at different conditions is called an amphoteric substance. That is amphoteric. And look at this. Here, HNO2 aqueous plus H2O. What happens if this is an acid, proton donor, this is acceptor, base. Similarly here, this is the conjugate base, this is the conjugate acid. Now, similarly, the same thing is explained with ammonia and hydrochloric acid with the electron distribution. How the electron is attracting. See, these electrons, they attract the H plus and the H plus come over here. So H3O plus is formed and these two electrons, they will get loaded on chlorine. So Cl minus is formed. Similarly for ammonia, here ammonia is the electron donor. Look here, water is the electron donor now. That is why it is on a base. Here ammonia is an electron donor, whereas water is an electron acceptor. So that is why ammonia is a base, water is an acid here. So on the basis of Bronsted and Lowry theory, this is explained. This is on the basis of Lewis theory. And if you look at a weak electrolyte dissociation, for example, acetic acid. When you take acetic acid, water is added. You know acetic acid is a weak acid. When the water is added, the H plus is donated by the acid. So water becomes an H plus acceptor, so base. But the problem is, its conjugate base is a strong base. This particular idea you should understand. This conjugate base is a strong base. When the conjugate base is a strong base, then its corresponding acid will be a weak acid. When the conjugate acid is a strong acid, its conjugate base will be a weak base. The idea is CH3COO minus is a very strong base. Therefore, it will not allow the system to lose the H plus ion. So the H plus ions are not easily lost from the acetic acid. That is why acetic acid is a weak electrolyte. But here, hydrochloric acid, if you take a Cl minus is having the completed octet. So it is a weak base. It is not powerfully attracting the H plus ions because it is stabilized. As it is a stabilized system, it is not pulling the H plus ion powerfully. Therefore, Cl minus is a weak base. That is why HCl is a strong acid. But here CH3COO minus is a strong base. That is why CH3COOH is a weak acid. So these are all the important idea behind the conjugate acid pair theory. Next, what are the differences between bases and alkalis? Base is not a proton acceptor, but it produces OH minus ions, which combine with protons to form water. So bases neutralize acids. Alkali, what is an alkali? Alkali are hydroxides, which will act as base in water. Sodium hydroxide is an alkali, but sodium hydroxide solution is basic. So there is a difference between base and alkali. So this you should understand. So next one is the Handerson-Hasselbalch equation. This is also we have seen already. Suppose if you take dissociation of a weak acid, so dissociation of a weak acid, HA getting dissociated to A minus plus H plus. And the dissociation constant is called Ka. Ka, that is the equilibrium constant of this dissociation equilibrium, is also called the dissociation constant. This Ka is equal to the concentration of H plus, concentration of A minus, and the constant divided by the concentration of the undissociated acid. Suppose if you take a logarithm to the base 10 on both sides, you get log 10 Ka equal to log 10 H plus plus log 10 A minus by HA. Now, suppose if you put a negative sign all over the equation, minus log Ka equal to minus log H plus minus log A minus by H plus. That is how it will come. And this minus, look here, this minus is pKa. See what he has done without introducing the minus, he has simply put a minus over here. So this is minus pKa, this is minus pH plus log 10 A minus by HA. This pKa can be brought out and the pKa can be put in. So pH is equal to pKa plus log A minus by HA. This is represented in a different form. pH of a buffer is equal to pKa of the acid plus log the concentration of the salt by concentration of the acid. The same Handerson equation can also be written for base. POH is equal to pKb plus log of salt by base concentration. So this is how Handerson-Hasselbalch equation is written. Next idea, what are buffers? Buffers. Buffer is a solution that resists pH change for the addition of small quantities of or small concentrations of acids or bases. Suppose if you take a buffer, and into the buffer solution, you are putting 2 drops of small concentration of hydrochloric acid or sodium hydroxide. Immediately, what will happen? Immediately, it will shift its equilibrium either towards right or towards left, depending upon the external force acting on the shifting of the pH, and it will adjust the pH in such a way the pH of the system remains unchanged. Such a substance is called a buffer. And this capacity, buffer capacity, it depends upon the actual concentration of salt and acid, actual concentration of salt and acid, and also salt to acid concentration ratio. So this we will understand in a simple problem which we have already done, but I will show it again. So buffers are weak electrolyte with its strong salt. It may be a weak acid with its salt, like acetic acid and sodium acetate, or a weak base and it's a salt like ammonium hydroxide, ammonium chloride. So these are all various buffers. Now you will see the importance of buffer. pH of the blood is 7.3 to 7.5. The variation, when it goes below 7 or when it is higher than 7.9, the effect will be fatal. So the buffering is always taking place in the biological systems. And various buffers are acting at various places of our body to maintain appropriate pH in various places. And the commonly used buffers in our laboratory are lactic acid and sodium lactate, which is used to buffer in the range 2.86 to 4.86. And the phthalic acid and potassium phthalate, which is used between the range 3 to 4 pH. And acetic acid and sodium acetate, 4 to 8. And also monosodium hydrogen phosphoric acid and the disodium salt of phosphoric acid, 6 to 8. So these are all the various buffers which are used. Now, so this is the problem I wanted to discuss. You can see, I'm taking lactic acid buffer, 10 ml, 0.1 molar lactic acid plus 10 ml, 0.1 molar sodium lactate. The pKa value of lactic acid is 3.86. So the pH I can calculate according to Handerson-Hasselbalch equation, and it is 3.86 plus log 0.1 by 0.1. See, the 0.1 concentration is directly taken because both are taken as equal volume. Even if you multiply volume and the concentration, these two factors will get cancelled. That is why it is written like this. So log 1 is 0. So the pH is 3.86. Suppose if I am adding 1 ml of 0.1 molar hydrochloric acid to the buffer, what will happen? That 1 ml of 0.1 molar hydrochloric acid will convert the sodium lactate into lactic acid. So what will happen? Sodium lactate volume will decrease to 9. That is, the concentration will decrease, but which can be considered as volume because the concentrations of lactic acid and sodium lactate are the same. So what will happen? That will be equivalent to 9 ml sodium lactate. And the more lactic acid is produced, which will be equal to 11 ml of lactic acid. That is, 1 ml of sodium lactate is now converted to 1 ml of lactic acid. So the new equation will be pH is equal to 3.86 plus log 9 by 11, which is equal to 3.77. So the change in the pH is 3.86 minus 3.77, which is 0.09. So what happens? When you take the lactate buffer, similarly, but I'm taking in a smaller quantity, smaller concentration. So 10 ml, 10 ml, I'm keeping the volume constant, but the concentration is 0.025, 0.025. Suppose in that situation, even then the buffer is 3.86 pH. But when you add 0.1 ml, sorry, 0.1 molar, 1 ml hydrochloric acid to the buffer, what will happen? That 1 ml 0.1 molar is equivalent to 4 ml of sodium lactate. So what will happen? that will pull 4 ml from sodium lactate and that will add the same quantity to the lactic acid. That is why the equation now becomes a 6 by 14. That is 10 now has become 14. 10, it has become 6 now. So the new concentration, sorry, the new pH will be 3.49. So if you find out the difference between these two, it is 0.37. Look here, previous case, the change in pH is just a 0.09 unit. In the second case, it is 0.37 unit. In the third case, I am taking different quantity, different concentration. Instead of changing the concentration, I have just changed the volume. So what happens is pH is equal to 3.86 plus log. I am taking 15 ml of 0.1 molar lactate and 5 ml of 0.1 molar lactic acid. Now the new concentration is 4.34. Suppose if I add to this system 0.1 molar 1 ml hydrochloric acid, what will happen? Again, the acid concentration, the salt concentration change. So the new pH will be 4.23. The difference is 0.11. If you compare the differences, in the first case it is 0.09. In the second case it is 0.37. In the third case it is 0.11. If you compare the variation is less in the case of the first one. So from this we are deriving at a conclusion that is a good buffering is observed when the acid and the salt are taken at higher concentrations. And the second observation is when the ratio is unity, then also a good buffering is observed. So these are all the cases which we have seen already. And I discontinue the class and please rejoin.